Okay, off we go. So, new chapter. We finished up chapter 3. We're skipping chapter 4 for the moment. Come back to chapter 4, kind of at the very end of the course. Short version. The reason for this is that y'all heard me talking about chapter 6 and 7. It's very challenging. There's a lot to talk about, a lot of perspectives and geometric interpretations. There's just a lot to do. My take is that we should try to get to that as soon as possible. The problem is practically everything in the course is prerequisite to it, and we can't move it, for example, to the very beginning of the course. So, chapter 4 is an easy choice to delay. It's not prerequisite to chapters 5, 6, or 7, so no cost to moving that to later. Okay, so on to chapter 5. This is about integrals. Y'all will recall chapter 2 is about derivatives. Y'all will recall the very first thing we did in chapter 2 is we talked about a easy, ultimately computationally convenient and useful, but also ultimately not really the best way to think about derivatives, namely partial derivatives. Nice tool, but ultimately there's a better and more sophisticated way to do things. It's practically the same story here in chapter 5. There is a first cut we're going to take. It is going to be computationally useful, but it is very convenient. It's an easy sort of first step, but by itself is pretty limited, and there is much better ways to think about integrals. Okay. All right. So y'all remember, I'm sure, this single variable calculus problem. If you have a rotated volume like this, how do you compute the total volume? And the idea is you kind of slice it up into a bunch of little, sort of coin-shaped little pieces like so. And then you notice that these coins have the feature that you can just look at the cross-sectional area, which is easy to write down, and multiply by the thickness. And area times thickness gives you volume, and that tells you how much volume you got in this piece, and then you integrate to get the whole. So I'm sure y'all have seen these kinds of problems. We're going to basically steal that idea to address a different problem, importantly different problem, and that is, suppose we're looking at a graph. Now, again, you got to keep in mind, what kind of a picture are you looking at? So, very importantly, these are graphs, and in particular, we're going to start with a function of two variables. That graph is a surface. We're going to look specifically at the part of that graph that is immediately above a certain given rectangle, and the question is, how would I compute this volume that's above the rectangle but below the graph? So you might even notice this kind of smacks of an old Calc 1 problem, which is area under a graph curve for a function of one variable. Here we're looking at volume under a graph surface of a function of two variables. Very analogous question. Okay, and so again, our first cut and a reasonable first thing to try, and it's going to kind of even work sort of, is we're going to look at sort of one slice at a time. And so, the visual that comes to my mind is, imagine this is a loaf of bread, and we slice it up into slices of bread, and the volume of the whole loaf is the sum of the volumes of the slices, right? I mean, pretty reasonable, kind of a shameless rip-off of exactly what we did here. Hopefully that's a pretty believable strategy. And so, okay, fine, we're just going to have to figure out then what the cross-sectional area is, and that cross-sectional area here, how are we going to compute that area? Now, in the Calc 1 problem, we looked at the cross-sectional area and said, oh, hey, that's a disk, pi r squared, right? Old convenient formula, boom, snap of the fingers, no problem. Here, well, that's not a disk, and it's not a square, and it's not a triangle, and it's not anything that we have a pre-existing high school geometry formula for. So here's the thing. It is area under a curve, and you can compute area under a curve with an integral. Is that cool? Is everybody with me so far? Okay. All right, now a couple things to say about this integral. You can see the picture of what we're looking at. Notice that we are finding the cross-sectional area for a given value of y. And notice a given value of y means y is fixed. That means y is constant. Y is not allowed to change. After all, it is for one value of y at a time that I need to know, well, okay, for that y, what is this cross-sectional area? Right? So as I compute this area, y can't change. It is therefore a constant. And so let's keep in mind, when I write down f of x comma y, that's representing the height here. Right? At very first glance, you'd look at this and say, whoa, hey, whoa, slow, this is a function of two variables. I don't know what's going on there. But very importantly, it's not. Right? Y is constant. While I'm doing that integral, while I'm computing this area, y is not allowed to change. And so let's color that in because y is constant. Right? In fact, this is just a function of one actual acting variable. Is that cool? Everybody with me? Okay, so it's all over but the shouting at this point. Let's see here. So the big picture, recall, is that we're going to let y go from c to d. Let me do it like this. We're going to add up as we go in the y direction. As we go in the y direction, we're adding up a bunch of little volumes, area times dy. Those individual volumes are areas times thickness, and the area we just computed is another integral. This area integral, of course, is an integral in the x direction because we go in the x direction to add up all the pieces of area that I have in light blue. So the weird thing about this computation is that we're doing an integral of another integral. And that's maybe the first time, I don't know, but possibly for many of you, probably the first time you've seen an integral of an integral. What do you think? Everybody all right? Okay. All right, so again, nice first step on this. And by the way, the little terminology that's called an iterated integral, because it's an integral of an integral. My little personal quibble with this terminology is we're not quite technically iterating because they're two different kinds of integrals. They're integrals going in different directions, right? So I prefer the term nested integral because it's literally an integral inside of another integral. I tried to popularize that term. It didn't go anywhere. So I think we're stuck with this term. It's not perfect, but it is what it is. So anyway, that's the term. Okay. Couple of things to remember. First of all, and I've already made a big deal out of this, but while you're computing this area, keeping in mind that area is that inside integral. While you're computing that area, don't forget y doesn't change, or said differently, the outside variable as it shows up in the inside integral, that outside that outside variable, you have to treat it as a constant. It literally is a constant for the purposes of what we're doing with that inside integral. Easy to lose track of that, but nice, pithy little summary. For the inside integral, the outside variable is constant. Okay. The other thing I want to mention before we go on, this is just a terminology thing, but it's tempting to call these integrals the first and the second. The problem is that as we develop this, the first integral that we write down is the integral in the y direction, where we argue area times thickness gives you volume and all of that. Arguably then the dy is first, and then of course the dx integral is second to compute the integrand of the first integral. But here's the problem. When you get to computing and you start looking at these integrals, all right, how am I going to compute these integrals? I kind of have to compute the inside integral first. I can't compute the outside integral first. I don't know what its integrand is yet. That's the whole purpose of the inside integral. It is the integrand for the outside integral. So you have to, well, I like to think of developing the integral anyway outside in, but you have to compute inside out. So this terminology, first and second, is very unclear. You may know what you mean when you say it, but your listener does not know what you mean when you say it, right? And of course, that's the purpose of language, right? Is that your listener knows what you mean, right? So I strongly advise against using that language. It's just not clear, and if we don't know what you meant, we can't give you credit for what you meant. Right? So I hope that makes sense. Okay, let's do one. Here we have a exactly the scenario that we just talked about. We're looking at a graph. Of course, y'all recognize the paraboloid, and that's kind of part of this larger paraboloid, but we're just looking at part of it. So there's our surface. We're looking over a particular rectangle. I'll talk about that notation in just a moment. And between that rectangle and that graph, we want to compute the volume like so. And again, we've already done the slicing argument. You don't need to reproduce this argument that we've already done. We have an iterated integral that we know will compute that volume for us. So we just write it down. The volume is this integral right here. Okay, now before we go on, let's talk about that rectangle. How do I know that that's the rectangle that means? What is the deal with that notation? It kind of looks like a cross product. The unfortunate reality is there's only so many symbols, and they get reused for different purposes, and you have to interpret in context, and it's a little tragic. But in this context, what this means is a rectangle where the first interval tells you the range of values of the first variable, in this case x, and the second listed interval gives you the range of values of the second variable, in this case y. So that notation refers to the rectangle where what I have in green is the sort of the x projection, and what I have in blue is the y projection, and you can see that's this rectangle. Does everybody follow? That it's a handy notation, very common notation, very convenient. We're going to be using it a lot, so I'll be on the lookout for that. Okay. All right, so it's pretty much plug and chug. Y'all know how to do single variable calculus. All of these integrals are single variable integrals, and y'all know how to do them. There's just a couple little sticky bits that I'm going to point out. Don't forget this inside integral. You can see the computation as it develops here of that inside integral. Big point, easy to forget. Common landmine that you can step on. The outside variable, you treat it as a constant. Super easy to mess that up. So for example, when you're doing these antiderivatives, right, you're doing x antiderivatives. The antiderivative of x squared is 1/3 x cubed. Sure, no problem. Just like you would think. But the antiderivative of y squared, you're going to be tempted to write 1/3 y cubed. You're going to feel that urge to write 1/3 y cubed. It's absolutely not. X is the variable. Y is further to the outside. That means y is a constant, and the integral of a constant is constant times the variable, namely x. What do you think? Everybody's good with that? Easy to mess that one up. Okay. All right. Second, this is just kind of a little, insurance policy, you might want to say. When it comes time to plugging in the bounds, we've got these bounds 0 to 1. And after you've done the antiderivative, of course, you take those bounds and you recopy 0 to 1. My little hack, trick, I like to write x equals in recognition that these are values of x specifically. And the reason I do that is otherwise, and you can possibly even imagine yourself, let's suppose that this isn't there and this isn't there. You could imagine yourself taking this value 1 and you plug it in, and you plug it in, and you might accidentally plug it in there for y, which of course it isn't. Which of course you can't, because y is constant. It's not varying from 0 to 1. It is literally constant for the whole integral. So that would be wrong. And I find that having this little reminder here, whoops, I wanted to change colors. Having this little reminder here helps me remember not to plug it in for the y. I hope that makes sense to everybody. You don't have to do that, but I think it's a helpful little personal ritual. If you follow this little ritual, then you'll make less, forehead slap. I can't believe I did that. Little whoopsies. Okay. All right. And compute. You'll notice that when you're done with that inside integral, the inside integral turns into that expression, which is a function of y. Well, there's two reasons. Of course it should be a function of y. Y was playing the role of a constant. It didn't do anything. It's not going to go anywhere, right? It's just going to sort of stay there as you go through the process. So, of course, there should be y's left over. The second reason that you know this should be a function of y is, again, don't forget what it is. It literally, right, this inside integral is literally telling us area as a function of y. How that cross-sectional area depends on which cross-section we're looking at. So, well, yeah, of course it's a function of y. What do you think? Everybody buying it? Okay, and then it's, again, more single variable calculus. That's no tricky curves on that one. That's just straight up Calc 1 integral. Okay. Now, this argument we just did, let's do it like this. This argument that we just got through talking about, we did our outside integral in the y direction. Said differently, I sliced up the loaf of bread this way. Reasonable question, can I slice it this way? And of course, yeah, absolutely. It's totally fine. Go ahead. Right? No problem. Now, there is an argument to be done, and you gotta redraw the picture and think through, wait a minute, what role is which variable playing at what stage? Details to be filled in. It's a fabulous little exercise. You can all do it. This will be your sort of model, right? Feel free to cheat off of this, right? But still gotta write everything down, and what you will find is exactly what you would hope. This volume that we previously computed, you might say dx dy. You can instead, if you like, compute dy dx. Is that believable? Again, blanks to be filled in by y'all. Again, healthy exercise. Do be aware of one thing. When you switch the differentials, a lot of times people think of this as just switching the differentials. It's not quite that simple. If you think about it, the differentials are paired with the bounds. If you switch the differentials, the bounds are attached to the differential, right? The bounds depend on which variable you're talking about. So don't forget to switch the bounds also, right? They go together. I hope that makes sense. Any questions about that part? All right. And a little bit of a warning. This is premature, arguably, but what I wrote here, warning, this only works if your domain's a rectangle. Now, of course, that's the only thing we've entertained up to this point. We've only looked at domains being a rectangle. You might anticipate we're going to consider non-rectangular domains coming up very soon. Probably not today. We'll see how time goes. But so Wednesday, guaranteed, right? And for non-rectangular domains, this idea of, you could just switch the bounds with the differentials, no, definitely not. 100% not. This does not work for non-rectangular domains. So that's a premature warning, but I didn't feel like I could make this comment without putting this warning in there. Okay. Everybody seems happy. Okay. I have some bad news. Something nice that happened in single variable is not going to work out. Certainly it's not going to work out conveniently, at a minimum, not conveniently. I would say it just doesn't really work out. So here's what I'm referring to. In single variable, we computed stuff like the mass of a rod, where you're given density as a function of x. You're given mass per unit length as a function of position. You want to compute the mass of the whole rod. Y'all have done these kinds of examples, again, back in Calc 1, I assume. And what tool did we use to compute the mass of a one-dimensional distribution of mass? Well, with this exact same integral we used to compute area under a graph. Exact same integral. Just wherever the f was, you put delta instead, and it's the exact same integral. Wasn't that nice? One could speculate then. Let's suppose we have a distribution of mass distributed over a two-dimensional region, and instead of computing the volume over that rectangular region, maybe we want to compute the mass in that rectangular region. And again, with a density given. Now this time, of course, density means mass per unit area, because it's distributed over an area. Well, golly, in single variable, it was the exact same integral. We just write it down. Boom, it works. What? Hopefully, one would think, one would hope, at least optimistically, maybe we could do the same thing here. And I'm sorry to report you can't. At least the argument as I just made it does not work. Let me explain why. It's about particulars. Here's our formula for computing volume that we just talked about. And let's look inside of here. Sort of implicit in the argument we made was that height times, height times length gives you area. Now, where does that come from? Why can I argue that height times length gives you area? Well, for golly, I mean, it's right here staring at us. Height, let's see here, let me do it with the colors. Height times length gives you area. Old news. That's what area is, and just boom, there it is. Let me point out, furthermore, not only do I know what that is, I know what area is, I know how it behaves. And I made this argument that this quantity, height times length, has the feature that the whole is the sum of the parts, right? I can compute this whole area as the sum of the individual slices of area. Area behaves like that. That's a nice feature of area. And of course it does. Okay. All right, so height times length is area. I know what area is, and area accumulates, by which I mean the whole is the sum of the parts, and so I can write down that integral. All right, that's all implicit in the argument that I just made, and does not work for what we would kind of hope for the mass example. And let's just kind of play it through, and let's see what do these things do. This density is mass per unit area. That's being multiplied by dx. Come on with the colors. Dx is length. What do I get when I multiply mass per unit area times length? And I don't know. That's not a thing. Right? So let's got to be careful about this. When I say mass per unit area, what I mean is this is a thing that if you multiply it by area, we can interpret it as mass. If you multiply it by something that's not area, no comment. Right? We haven't developed that idea. And when mass is distributed over area, you might be tempted to call this product mass per unit width. But mass isn't distributed over width. I'm not entirely clear what we might mean by saying mass per unit width. And even worse, even if I could make sense out of this, and by the way, don't get me wrong, I could make that happen if we had to. But once I have that as a concept, do I know that this is something that accumulates? Can I just argue that the whole is the sum of the parts for this brand new concept that we never even physically thought of before 30 seconds ago? I don't think that's clear. Everybody see the problem? It just kind of breaks down. The argument just doesn't make sense. Okay, so that's the bad news. Here's the good news. The good news is we don't need this argument to make sense. There's a much better way to approach all of this stuff that we're doing. Even what we did here, look, it's going to play a role at the very end. It's going to be kind of convenient, but ultimately, even this is not really the point. So, bad news that it doesn't work. Good news is we don't need it to work. Okay. What do y'all think about that? You buy it? Any questions on that? Okay. Okay, so that's 5.1. Moving along, 5.2. Y'all remember single variable calculus. I know you know single variable calculus. That said, many students, myself included, when I was about y'all's age, coming out of a single variable calculus class, many students have a fundamental misunderstanding of what an integral really is, and this matters. This is not just, mathematicians enjoy getting fussy and upset about formalities. Now, don't get me wrong, we do. But that's not the point. That's not the pitch that I'm putting on y'all. I claim that for application purposes, if you want to solve real-world problems, if you want to talk about where the rubber meets the road, it's very important that integrals are Riemann sums, not area under a curve, in terms of the definition. Now, yes, one of the many applications of this expression is that yes, you can compute area under the curve with this, but that's not the point. The point is, what are we making the definition of an integral? Okay, so I'm sure you all have seen this expression before and related details. Make sure you're crisp with all of this stuff. It's just unavoidably what we need to understand. Let me try to persuade you why, and I'm going to try to keep this brief because, we're always in a hurry. But also, I have an extensive, detailed discussion of this in that miscellaneous topics playlist. And if you want to hear more about why this is really important, even for single variable calculus, even for application purposes, I encourage you to go watch that recording. It's called "What is an Integral?" and it's again in the miscellaneous topics playlist. Suit yourselves. Here's the argument I'm going to make here. When you want to compute something like, let's say, mass, any of a great number of applications, I just listed a handful. There's bazillions more, of course. If you want to compute something, what we do is we break it down into a Riemann sum. You take a one-dimensional rod, right? Mass distributed over an interval, one-dimensional interval. Chop that up into little pieces. We compute the mass on each individual little piece. Mass per unit length times length on each individual little piece, and then we add up over the interval. And notice, nowhere in that argument did I say the word area. There's no area in that argument. There's no area in that question. Why would we bring up area? Right? So, now again, this quantity, I can break it up into little pieces and add them up. Riemann sum is made perfectly to address that. No problem. Define integrals as Riemann sums, compute integrals with the fundamental theorem of calculus. Boom, victory, we move on. No area needed. Now, the awkward, doesn't really hold water take that I hear sometimes is, mass is area under a certain curve, to which I ask, why? Explain that to me. I don't get that. How does that make sense? Mass is in units of grams. Area is in units of square meters. Those are not the same units. They're not the same stuff. They're fundamentally different quantities. What do you mean they're the same? It's not clear. right? Now, here's the argument that I saw in high school. And it was, well, yeah, sure, but you can take those masses and you can chop them up into little pieces, and when you draw the graph and you look at the blah, blah, it basically kind of did everything but a Riemann sum argument. Just didn't quite say the word Riemann sum, right? And then concluded that mass is equal to area. Give me 2 seconds. And then having computed that, or having argued that mass was area, computed that area with an integral. And I just make the argument here that area, this was an unnecessary digression. This little detour to, yeah, but we want to say area. It doesn't play a role. It's not necessary in the argument. Yes?
Wouldn't density be like kind of like the antiderivative mass, like the area under a density curve?
I mean, we want to distinguish between what's true versus what's clear, right? And so, yes, the area under the density curve is the mass. The question is why. And the reason why is, if I may, that mass can be written as a Riemann sum. The area that you're referring to can be written as the same Riemann sum. And so I can therefore say, well, then, by the way, in this case, I can think of mass as being area. And to which my counter is, we already had it as a Riemann sum, we don't need area. Does that make sense? Yeah. So it's not that it's wrong, it's that it's not a necessary element of the clear argument. Yeah. Okay. And I know a lot of high school classes like to de-emphasize Riemann sums. I managed to walk out of my high school calculus class with this, in retrospect, obviously nonsensical impression that Riemann sums were outdated and obviated by Newton's discovery of the fundamental theorem of calculus for computing integrals. I thought, okay, well this is the old way to do it, and instead, much better, we'll do it with integrals. Now that doesn't even make chronological sense. Riemann wasn't even born yet when Newton came up with the fundamental theorem of calculus. So it's just not accurate. All right. So again, the reason this matters, okay, this is not a pure math. This is not a real analysis, measure theory class. This is not Math 531, right? But the reason this matters to y'all is that y'all are going to be doing lots of applications. The rubber is going to need to meet the road. And if you want to compute whatever work, maybe, whatever it is, the point is you're going to be writing it down by chopping it up into little pieces, and on each little piece making an argument about how to compute on each little piece, and then adding up those pieces. That is literally and exactly what a Riemann sum is. And in each individual case, having to go to the additional unnecessary trouble of, but I want to think of it as area. I mean, again, suit yourself, but it doesn't actually serve a mathematical purpose. Yes?
So you're going from like mass when you work.
Uh-huh.
And you want to break it up into proposed theory stuff. Don't you still need to know that the base function, the antiderivative, the base function that would get you to mass? Don't you still need to know that's density or that's the negative potential energy for work?
I'm not following. Say it again.
So when I'm making my Riemann sum, don't I still need the base function? If I wanted to find the mass.
You're talking about the integrand?
Yeah.
Well, yeah, of course, absolutely. And so when we write down, let's take a mass example just because it's physically a little bit easiest, right? I say on any individual little piece, let me draw a little interval here. Here's an interval from A to B, and I chop that up into a bunch of pieces. And let's talk about on this piece right here, that little piece. When I write down its corresponding term, I'm absolutely going to need to know that if I want to compute mass, I'm going to need to know what is the quantity per unit size, that I will then multiply by size. My point isn't that we don't need that function. My point is that we don't need to draw the graph of that function and think of it in terms of areas. Does that make sense? Yeah. Yeah. Absolutely. Okay. All right. So if you want more on why Riemann sums are important, you got that YouTube recording at your leisure. By the way, the reason I'm making a big deal out of it here is not because I want to. It's partly because I want to solidify your understanding of single variable, but mostly it's that if we're going to generalize the idea of an integral, we have to be very clear on what is this thing that we're generalizing. We have to generalize the right thing, right? And Riemann sums are the right thing that we need to generalize. Okay. So lots of different situations, and kind of to the question that you just asked, when you have an interval like this, and you chop it up into a bunch of little pieces, and on each little piece, we're always going to do a little calculation kind of like this. Every application is different. If you want to compute mass, I want to know how much mass is in this piece. My integrand is mass per unit size, which I then multiply by size to get mass, which I then add up. If I want to compute how much work it takes to go, across this little piece of my interval, well, then I'm going to need to know work per unit size to multiply by size to get work, and then I add up all those pieces of work. It's always going to be, the integrand is always going to be whatever my relevant quantity is per unit size, so that when I multiply by size, I get the quantity that I then add up. Okay, so we're going to now try to do the same thing, but for a two-dimensional rectangular region. Same basic idea. And maybe there's mass distributed across here. Maybe it takes a certain amount of work to, maybe I'm picking weeds, possibly. And it's going to take a lot of work to pick those weeds, and I want to keep track of how much work I'm doing or how much my back is going to hurt, whatever, right? And, okay, well, golly, there's more weeds over here and there's less weeds over there. Whatever it is, on each individual piece of the yard here, I'm going to need weeds per unit size to multiply by size. That'll give me weeds that I then add up over the whole yard. Or if I want to compute mass, okay, well then I'm going to need mass per unit size to multiply by size to get mass. And I add up all the mass. Same basic construction. It's just that now it's area is my size, because that's a little piece of area, as opposed to over here, length was my size, because this is a little piece of length. What do you think? Everybody see where we're going with this? All right. Yeah, so on each little piece, just to keep the analogy clean, it's always quantity per unit area to be multiplied by area to get quantities. All right. And then, by the way, of course, there's a lot of little micro details here, right? If you slice up this region every which way, like so, notice that in that process, you're also slicing up both the x-axis and the y-axis. Right, and in the same way as slicing up the x-axis gives you these rules for delta x and x sub I, likewise, slicing up the y-axis will give you these rules for delta y and y sub j. And so then, with those formulas, then when you talk about, on any one of these pieces, on any little piece of area, when I need to evaluate the function, I evaluate the function at a point xi, yj, whose coordinates I have formulas for. That's just to make it precise, exactly what do we mean by the Riemann sum. Here's the good news: in practice, we're not actually going to be computing with this. The important thing is that underlying every double integral we will write, this conceptually is what we mean when we write down that double integral. It's always going to be stuff per unit size times size, namely area. Okay, so that's our definition of a double integral. This two-index Riemann sum where both I and j vary from 1 to n. This Riemann sum is what we mean when we write down a double integral. This is our notation for a double integral. I think the notation is pretty believable. Whatever your integrand is, you write down your integrand. dA, well, delta x, delta y, is to represent little pieces of area. In this book, and in most introductory books on multivariable, and in, I think most books on like physics and engineering, I don't want to speak too broadly, we use two integral symbols because we're adding up both I and j, namely we're moving in two different directions because ultimately it is a two-dimensional domain. And so the two integral symbols is kind of a recognition that it's two indices in two dimensions. That said, in advanced math books, just FYI, they don't bother. In advanced math books, they'll put just a single integral symbol, and it is understood that it is the reader's responsibility to interpret appropriately to what the dimension of the domain actually is. Like whatever, here we're adding up over a rectangle, right? So R is this rectangle. All right, well then, yeah, rectangles are made up of area. We're doing pieces of area. Clearly this is a double integral. Right? And so you might see at some point a single integral symbol there instead of two. We're not going to do that in this course. Okay. Alrighty. Let's see an example of this in action. A question we already know the answer to, but let's do it anyway. Suppose we have a graph. And we're looking at a particular rectangle, and over that rectangle and under that graph, we want to compute the volume. All right, well, again, we already know how to do this, right? An iterated integral would solve this problem. Here, we're going to deal with it differently. Here, I'm going to say we're going to take our domain. We're going to chop up our domain into little pieces of area. I'm not slicing to make, slices of bread. There's no bread in this computation. We're going to look at little pieces of area, little sub-rectangles of our domain. Over every sub-rectangle, there's a little piece of volume. A little French fry. Height times area of the base gives you that volume. Right? By the way, glass smooth. No funny business with volume per unit area times. I mean, it's just that's what it is. Volume is height times area of the base. Straight up. And then we recognize, oh my gosh, look at that. That is the exact definition of a double integral. And so, boom, double integral. Yep.
Does this still require the domain to be a rectangle?
Yes, for the moment, all rectangles. Yeah. And we'll consider non-rectangular domains later. Yeah. Everybody on board? Okay, a silly exercise, arguably, because first of all, we already knew how to do this. Iterated integral would totally do this for us. Second of all, we don't even have any methods for computing these double integrals. Right now, as of the moment, these double integrals are just Riemann sums, and it's not that we can't compute them, it's that we really, really don't want to have to compute directly from these expressions. Y'all remember computing directly from Riemann sums? And yeah, it's brutal. It's super inconvenient. Nobody wants to do that. Okay. All right. So here's why I like that example. It's a strategic move. This is a kind of a strategic diagram of everything we've talked about so far. I'm going to rewind to the very beginning of today's lecture, talk about everything we've done in today's lecture. We started off with the question of how do I compute volume under a graph? We argued that it was an iterated integral. That's a slicing argument. That's the loaf of bread is the sum of the volumes of the slices of bread. And then we can compute the iterated integral with the fundamental theorem. That's all, okay. And then I argued, yeah, but this is what we really care about. Volume under a graph, to be totally honest, doesn't come up that often. It's not super common that in an engineering, every so often, yeah, sure. But most of the time in an engineering context, a physics context, you're computing something like work or mass or something like that. And you just can't immediately make it, let me do this in red to be clear, we can't do this. You can't just immediately argue that mass is an iterated integral. As you try to make that argument, the units don't work out. You're bringing up quantities that we don't know what they are. We have no intuition for how they behave. And then you're making claims about them. It's not a clear argument. And of course, mass is not, in fact, just volume. So those we can't do. So the big payoff of the idea of a double integral is this. First of all, I can write lots of different things as double integrals. We're going to see several of them, over the next few days. Mass will be our first one coming up real soon here. We're going to be able to write them as double integrals. And we just got through arguing that volume can be computed with a double integral. And here's the role now that volume has served. Volume has done a very nice thing for us. Thinking about volume, I've computed it two different ways. It is, after all, though, one thing. There is only one answer to what a given volume is. So when you compute it two different ways, the two things that you get are the same. And that's really the big payoff. So now this is kind of the roadmap of arguments that we've made, and now you can see, we don't need that, we don't need that, and frankly at this point we don't even need that anymore. This is how we're going to solve problems. It's this three-step process, and just to summarize, so first step, whatever our application is, write it as a double integral, not as an iterated integral. That doesn't make any sense. Write it as a double integral. Second, recognize that double integrals can be computed with iterated integrals. After all, they both compute the same thing, namely volume. And then third, take that iterated integral, punch it up with the fundamental theorem, and there's your answer. So there's our three-step process. How are we doing? Is everybody on board? All right, so last observation on this page. And I know y'all heard me say this a million times. It's so important, right? This is not a class about answers. It's a class about ideas and reasoning, right? You got to show your arguments. Your reasoning has to be mathematically valid reasoning, right? I'm not just going to look and see if you got the right answer, right? So a problem is that very often students are like, I don't want to write down the double integral. That's not, I'm just going to work with the iterated integral anyway. Let me just not write down the double integral. And the problem is, by not writing down the double integral, your argument is effectively this. Which again, it doesn't make sense as an argument. Yes, it gets you to the right answer. This is not a course about answers, right? This reasoning doesn't make any sense. At best, it's got big gaps, and those gaps would have to be filled in. Right? So not writing down the double integral means you're literally doing this, and that's just not valid. So here's the good news. The good news is writing down the double integral is easy. Hardly anything to it. It's just a little doff of the cap to recognize that we need that two-index Riemann sum. That's all it is. And we've got an example incoming. Let's see, are we good? I don't think we're going to have time to do that example, but the very first thing we will do next time is talk about an example of this three-step process, and you'll see how easy it is to write down the double integral, and then you get full credit. All right, see y'all later. Have a good rest of your Monday. Yeah, see you.